In section 5.4, we're going to learn about one set of formulas called the sum and difference formulas. We're going to learn how to use them, first of all, in examples 1 through 3 to find sine, cosine, and tangent of angles. And typically, these are going to be angles that do not fall on our unit circle. We're also going to use them to verify different trig identities. That's going to be in examples 4 and 5. And we're going to solve trigonometric equations involving more complicated arguments. So that's example 6. So you'll see below, I listed the sum and difference formulas for sine, cosine, and tangent. You can look on the left-hand side. The argument is a sum of two angles, so u plus v or u minus v would be the difference. And then we have these kind of complicated formulas on the right-hand side that tell us what the equivalent formula would be. So make sure you go to your formula sheet and mark down which ones these are. So label your formula sheet sum and difference formulas. I think it's the bottom right box. And if you're interested in a proof for these formulas, you can see page 424 in your textbook, and they'll walk you through kind of how these formulas got derived. And if you have any questions, let me know. So our first example is to find the exact value of cosine of 75 degrees. Now, if we were going to try to find this, it's not on the unit circle, right? And if we plugged it into our calculator, we would get a decimal. It wouldn't be exact. So what we need to do is use a method, use these sum and difference formulas to try to evaluate it exactly using unit circle values that we do know. So let's notice that 75 degrees is 30 degrees plus 45 degrees. So if we're evaluating the cosine of 75, we can use the sum formula for cosine. So that's cosine of a plus b equals cosine a times cosine b minus sine a times sine b. And now what we actually have is cosine of 30 degrees plus 45 degrees. So we're just going to plug those in for a and b. So this is cosine of 30 times cosine of 45 minus sine of 30 degrees times sine of 45 degrees. And this comes off our unit circle. So 30 degrees has a coordinate of root 3 over 2, 1/2. And 45 degrees has a coordinate of root 2 over 2, root 2 over 2. So we're going to plug those values in. This would be square root of 3 over 2 times square root of 2 over 2. And then we're subtracting off 1/2 times the square root of 2 over 2. We'll combine our radicals, root 6, and then minus root 2. Now these are both over 2, so we can write it as one big fraction, root 6, minus root 2 all over 2. So that's going to be your answer. Remember, we can't add or subtract radicals. Only multiply or divide them. So we can't simplify this anymore. Now you notice if you plug this in your calculator, you're going to get a messy decimal that you wouldn't be able to just look at and know, oh, it's root 6 minus root 2 divided by 2. So our next example is finding the exact value of sine of pi over 12. And again, pi over 12 is not on our unit circle. So what I'm going to recommend doing is let's look at that first quadrant of angles. And we've got 0, pi over 6, pi over 4, pi over 3, and pi over 2. So I'm going to recommend, let's write these with denominators of 12. So pi over 6 becomes 2 pi over 12. Pi over 4 becomes 3 pi over 12. And pi over 3 becomes 4 pi over 12. Okay, so we notice these all differ by pi over 12, which happens to be 15 degrees. So we can pick any of these two and then just subtract them from one another. Because we have sine, we're going to use sine of a minus b, and that's equal to sine a times sine b. Oops, I'm sorry, wrong formula. Sine of a times cosine of b and that's minus cosine of A times sine of B. So just because they're smaller values, I'm going to pick pi over 6 and pi over 4. So the sine of pi over 4 minus pi over 6 is equal to the sine of pi over 4 times the cosine of pi over 6, and then subtracting off the cosine of pi over 4 times the sine of pi over 6. And we'll find these off the unit circle. We get root 2 over 2 times root 3 over 2 minus root 2 over 2 times 1/2. And similarly as the last problem, we combine these, we get root 6 minus root 2 all over 2. Okay, and an alternative form that we could write that you'll sometimes see in the book. So our alternate form factors out the square root of 2 over 2 from both of these terms. And, oops, I'm sorry, your denominator here should be 4. That's my mistake. It should be a 4. So here, if we wanted to, instead, we could factor out a square root of 2 over 4 from both of these terms. And that's going to leave us with root 3 minus 1 in the parentheses. So sometimes you'll see that in the book. I just realized I made the same mistake in the previous problem. Our denominator in the previous problem should also be 4. So example 1 should be square root of 6 minus square root of 2 all over 4. All right, let's move on to example 3. Find the exact value of sine of 42 degrees times cosine of 12 degrees minus cosine of 42 degrees times sine of 12 degrees. So here we're going to work right to left, and we want to find out which identity does this look like. Well, it looks like the difference formula for sine. So sine of A minus B equals sine of A, cosine of B, it's the one that we just used, minus cosine A, sine B. So on the right-hand side is what we're given, sine of 42 degrees, cosine of 12 degrees, minus cosine 42 degrees, sine of 12 degrees. On the left-hand side, we just get sine of A minus B. A is 42, B is 12. So 42 degrees minus 12 degrees turns out to be sine of 30 degrees, which is great because that's the unit circle value that we know. And the sine at 30 degrees happens to be just 1/2. So that big messy formula we started with turns out to just be 1/2. So those first 3 examples are finding exact values for sine, cosine, and tangent. We didn't do a tangent example, but they work very similarly. We can also use these to prove or reduce formulas. So we're going to prove one of the cofunction identities from section 5.1. This turns out to just be using the difference of cosines. So we get cosine of pi over 2 minus x is equal to cosine of pi over 2 times the cosine of x plus sine of pi over 2 times sine of x. And we'll plug in our values. At pi over 2, if we look on our unit circle, we've got the coordinate 0, 1. So the cosine is 0, 0 times cosine of x, and the sine is 1, 1 times sine of x. This first term just cancels out, it's 0, and then we're left with sine of x. And that happens to be exactly what we wanted on the right-hand side. So similarly, when we use this formula to rewrite our complicated argument, theta minus 3 pi over 2, we want to come up with an expression that only has sine of theta or cosine of theta, where our argument is just that unknown angle. So we're going to simplify this by applying our difference formula for cosine. So we get cosine of theta minus 3 pi over 2 equals cosine of theta, cosine of 3 pi over 2, plus sine of theta, sine of 3 pi over 2. This happens to be a similar angle, but now we're in the negative y-axis, so 0, negative 1 would be our coordinate down here. So we're going to get cosine of theta times 0 plus sine of theta times negative 1. So again, this first term is just 0, and we're left with negative sine of theta. And you can see at the end of the day, our function only has an argument of theta. So we simplified that kind of messy argument to be just negative sine of theta. So our sixth and final example is finding all solutions to this kind of complicated trig equation where we have x plus pi over 4 as an argument. We also have x minus pi over 4. So I'm going to find those two expressions separately. Sine of x plus pi over 4, plus pi over 4. And that would be equal to sine of x cosine of pi over 4 plus cosine x sine of pi over 4. And I'm also going to find the sine of x minus pi over 4, because we're going to be adding these two terms together. So here we get sine of x cosine of pi over 4. The only change in the formula is that it's minus, so minus cosine of x sine of pi over 4. And what we're going to do is the left-hand side is just adding up these two left-hand terms. So if we add up the right-hand terms, which are the expanded terms, we should get a negative 1. So I'm going to add up. We get two of these terms, 2 sine x cosine of pi over 4. Now we have the positive and negative of the same terms. So this would just be 0, and that's equal to negative 1. So we end up with 2 times the sine of x times the cosine of pi over 4, which is root 2 over 2, all equal to negative 1. So here I'm going to cancel my 2's. I get sine of x times root 2 equals negative 1. We'll divide by root 2, and we end up with sine of x equals negative root 2 over 2 once we rationalize. So looking on a unit circle, well, sine is negative in quadrants 3 and 4, and we should recognize root 2 over 2 from a unit circle being one of those pi over 4 increments, so it happens to be 5 pi over 4 and 7 pi over 4. So there's two answers between 0 and 2 pi. Exactly, these are x equals 5 pi over 4 and 7 pi over 4. So that's all for now. You can see on this next page, the Now You Try problems, there's a couple of each type of problem. So some of them, the first two are exact values. There's one identity to verify using the difference of tangent, the difference formula for tangent, and then one of those solving problems like example 6. So give those a shot and bring your work to class.